So here we would be doing a complex numbers. I will be explaining the concept of complex numbers. The first definition was not an imaginary number. An imaginary number is given by this: I squared is equal to -1. Then complex numbers, we know that can be written. We also have what we call complex numbers. They can be written in the form of a plus bi, and then we said I is our imaginary number, where I squared will be equal to -1. So we've got the addition and also the subtraction of complex numbers. So I'm going to write the examples under this. We have the addition and subtraction. Number 1, given that z is equal to a plus bi and w is c plus di, we can perform the addition of z plus w. This will just give us a plus c plus bi plus di. So you add the real numbers together and the imaginary numbers together. So this will be a plus c plus, I can take out I, then this will be the same as, so this will be our final answer. And then we can also do z minus w, then this will be bi minus c plus di. This is our w, and this will be a minus c plus bi minus di. So same thing, we'll group the real numbers together and the imaginary numbers together. So you'll have this as your final answer. And given if z is equal to 7 minus 2i and w is -4 plus 7i, z plus w would be 7 minus 2i. If I'm performing the addition, this will be like this. Then you'll just get 3 plus 5i. Then we can also, let's take this somewhere, and also perform the subtraction again. Using this example, you can also do z minus w. So this will be z 7 minus 2i minus -4 plus 7i. And this will be 7 minus 2i plus 4 minus 7i. Then this will be 3 minus this will be 11. 7 plus 4 will be 11. Then minus 9i. So this one is for z minus w. Then now if we were doing multiplication z w, so you have 7, you have that, and you also have this one. So you just multiply, but let me use a different example. Suppose you have your z as a plus bi and your w as c plus di. So if you are doing a multiplication, remember this form we said we are calling, this is called complex numbers. So they are in the standard form of a real number plus imaginary number. Then now we're doing the multiplication of this. This will be AC plus ADI plus BCI plus I times di. Obviously, this would be bdi squared. And this will be minus bd. Remember, we must replace I squared with minus 1. Or let me just do it like this. And we're going to group the real numbers together and the imaginary numbers together. So you'll have AC minus BD, AD plus BCI. So that's your final answer. We can also perform division. But if you're performing division, our Z is A plus BI, our W is C plus DI. For us to successfully do this, you must multiply by the conjugate. So the conjugate here, you will multiply with C minus DI, and this will give us A plus BI, C minus DI, and then C, this will be C squared minus D squared, I squared. And we know very well that this I squared, we are going to replace it with negative 1. So we're having this. All over C squared plus D squared. Right, and then obviously from here we can want to take the simplify this part as well. So this will be AC plus it will be minus ADI plus CBI minus DBI squared all over C squared plus D squared. So let's write this on the new page. So this is what we're currently having. Then you realize that this will be AC minus A plus C, or this will be AD plus CB, and then I take out I minus, this will become plus BD if you replace C squared with negative 1, and all over C squared plus BD squared. And finally, this will be AC minus U plus BD. So I'm going to separate the real number with the real numbers, and then the imaginary part with this. So I'm having this basically. So we can clearly see, now clearly see, and this will be plus, and then we can put the minus here. So this will actually give us AC plus BD over C squared plus B squared plus BC this will be plus BC minus AD I c squared plus d squared. So this will be the final answer. So you rationalize, that's the key word. You rationalize whenever you're doing the division of two complex numbers. You can even rationalize twice. I believe you're gonna get the same answer, meaning I could have multiplied here by a minus bi, a minus bi, and also this one. So at the end of the day, you should get, as long as you are still getting a plus bi, you have your real part and then plus your complex part, or let's say the plus your imaginary part, not complex but imaginary part. So suppose now I'm having z, if z is 5 minus 2i, w is negative 6 minus I, then z over w would be given by this. Then I can rationalize. Then this will be 5 minus 2i, negative 6 plus I all over negative 6 minus I. So this will give us, let's write this on a next page. So this will give us a negative 30 plus 5i plus 12i minus 2i squared. After simplifying, then here you'll have 36 plus 1, plus 1, which will be, then this will be 17i minus, this will be plus 2, then all over 37. Then we can clearly see that you just have negative 28 plus 17i over 37. Then this will be negative 28 over 37, 17 over 37i. Now we'll come to the next one. Suppose they say simplify the following. I 2 plus 5i all squared. This will be I 4 plus 20i plus 25i squared. And then you simplify this. Then this will be negative 20 minus 21i. Right. Then b, suppose they say simplify this imaginary, this complex number here, 4 minus 3i. So obviously here you'll have to first simplify this part, the numerator. Then you'll have 2 plus 2i minus I minus I squared all over 4 minus 3i. 2, this will give us 2 plus, this is 1. Remember, this is the same as minus negative 1. So we're having plus 1 plus I. This will give us I, which is this I. And then you'll have 4 minus 3I. Or perhaps let me do this step by step. So I'm having 2 minus I squared plus 2I minus I, 4 minus 3I. So these two together, this will be 2 minus negative 1. And this is the same as 3 plus I all over 4 minus 3I. Then from here, we'll have to rationalize this, so that we can have what? A plus bi. Remember, we don't want a fraction. We want this to be in this standard form of a complex. This must be an element of complex numbers. So after rationalizing So let's see what we're gonna get. This will be 16. You'll get 16 plus 9. Then this will be 3 plus I. So let's simplify this. This will be 12 plus 9I plus 4I plus 3I squared, 25. And this will be 12 plus 9I plus 4 plus, and this will be minus 3 all over 25. Then we'll just have 16 minus 3 plus 9I over 25. And this is just 13 plus 9I. Then you have 25. So basically, I will be having 9I over 25 plus 13 over 25. So if you guys have questions, you are going to ask. So I'm checking the next one. So I'm actually using these very same examples on your slide. So I was currently doing this one. Then we got this. And then now for this one, I'm gonna also do it here. So this will be number 3. Suppose you're given I squared minus I cube minus 2 over I5, I to exponent 5. You can see this is the same as -1. We know that we can change this to be I times I squared. Then we're having minus 2 over, so this is I squared to exponent 2. So this will give us I to exponent 5 again. And then this is -1 minus I times -1 minus 2 over I -1 squared. And this is the same as plus I minus 2 over I times 1. And yeah, this will be 2 over I. Right, then here we'll be forced to, we'll have to rationalize this part. This will be times I over I. Then this is -1 plus I minus 2I over I squared. Then this is -1 plus I minus 2I over -1. Then this will change to be positive 2I. Then I'm just saving -1 plus 3I. So this is our final answer. I wanna write it. So this is my final answer. So I was doing the last one there. Then if this is solved for x, and y, number 1, you are having 3. Obviously, you'll simplify this. Then you group the imaginary with the imaginary. So we know I'll have 3x minus 3 minus 5 minus 3iy plus 9i equal to 0. So now we can take so remember the imaginary part is supposed to be equal to the imaginary part, and the real must be equal to the real. So that's what we're going to do. So I'm going to take the imaginary part again to the right. So this is going to be 3x must be equal to 5. Because if we're having this, we won't be able to proceed. Or we could have equated it directly from here, from this step. So I'll have 3x is equal to this 5. And also negative 3iy equal to negative 9i. Then this will be x is equal to 5 over 3, and the i's here will cancel. Then you'll have y is equal to 3. So I've managed to solve. Then b, you are having 3x plus I2y minus 2x minus iy. So you simplify this. This will be plus 2yi, 7 minus 16i. So I'm having on the left, if you simplify this, you'll have x plus 8yi is equal to 7 minus 16i. So you'll just equate x will be equal to 7. You equate the real part with the real part and the imaginary part with the imaginary part. So you'll have and 8yi is equal to negative 16i. Then you divide by 8i over 8i. Then y will be equivalent to negative 2. So you have your x and y. Number C, if you have 3 minus I is equal to root of x plus iy. This will be, I can square both sides. Then I'll have 9 minus 6i plus I squared x plus iy. Okay. So let's open a page. So this will be 9 minus 6i plus I squared. Then the square will get cancelled. So I have 9 minus 6i minus 1 x plus iy. This is the same as 8 minus 6i x plus iy. Then we equate the real part with the real part and the imaginary part with the imaginary part. So actually x is gonna be equal to 8 and our y will be equal to negative 6. Remember, you'll equate this. Then you divide both sides, you'll just have y being equal to negative 6. Then now I'm gonna move to the properties that you must know on complex numbers. So we're going to let ZW be complex numbers. So the first property, Z plus W is the same as Z plus W plus Z. This is there by the commutative law. By law of commutative, ZW is the same as WZ. Multiplication, commutative law. C, and then you also have the associative law. D, ZW. Then this is also multiplication, associative, and then this one is addition, associativity. So I'm trying to summarize this quickly. Then E. So this one will be distribution law. By the law of distribution, then you also have Z plus 0. It's the same as this. So this is by addition law, or we can say is the identity law. By the law of identity, this is equal to that. Anything plus 0 is that number. Then also have the additive inverse law. So you get this. Let me not put this. And this is additive by additive inverse. Then the last one, 1 times z is equal to z, multiplication law. Okay, so these are just some of the things that you must know. So also have what we call a modulus argument polar form. So you are going to let z be equal to a plus ib. So this is a complex number or expression. So we're going to say the magnitude of z, we know that it's going to be a squared plus b squared. Magnitude of z. So the polar form of this complex number is going to be given by r cosine of theta plus ri, the sine of theta, or you can write it like this, cosine of theta plus I sine of theta, meaning that the magnitude of z, r is equal to the magnitude of z. In other words, this is equal to a squared plus b squared. So the coefficients. So in this case, it means you'll be having cosine squared of theta plus sine squared of theta. And then you just have 1. Since that's a trig identity, then our r will be 1. So meaning in this case, our r is 1. Then the formula will just update to this. So this is the polar form. Example 1, or let's just say examples. They say find the modulus and the argument of the following complex numbers. Number 1, so here you'll have to know the table or the graph where z is going to be positive, because in this case we want to write this complex number in its polar form, and you're gonna get something like this. So we'll be forced to we must look for the angle. So in order to get the angle, you must draw a Cartesian plane, and this is called the Diagat diagram. So we've got where z is equal to where our theta is equal to 0. We have where theta is equal to the arctan of b over a. So this is on the third quadrant, minus pi. Then on the second quadrant, we've got this plus pi. We add pi. So this is equal to theta. And then here, theta is equal to what? I think theta is just equal to pi, but let me first confirm. Z is on the negative. Will be less than 0. Okay, so in this case, on the positive axis, I'm sure we can all agree that this is where b is equal to 0 and a is greater than 0. So if you have such a scenario, your theta would be equal to pi over 2. And then when b is less than 0, which is this part, and a is greater, and a is equal to 0, our theta will be equal to negative pi over 2, but we'll discuss what happens on the fourth quadrant. For now, we're just going to follow this. We check this one, z equal to 1 plus I. We check what we're going to have as our theta. So let's come here. So this is in the form of a plus bi. So you can see a is greater than 0 and also b is greater than 0. So this is on the first quadrant. So on the first quadrant, on the Agathe diagram, on the first quadrant, you'll just have arctan of b over a. So meaning that this will be, theta will be arctan of 1 over 1. Then you'll get, let me see what you'll get. So we'll get a pi over 4. So that's our theta. Then z will be r. Remember, this is the format. And you'll have what? Cosine of pi over 4. Pi over 4. So now we want to find the value of r. So it will just be I squared plus 1 squared plus 1 squared, which will be the root of 2. So just say this is a root of 2 cosine pi over 4. So you can further simplify this if you want, but we're going to leave it in this format. So this is our z. So you can try doing the one whereby you have z equal to I, and then you'll find that your answer is equal to this. So this will be exercise 1. And exercise 2 will be, let us see, if you are given z is equal to -1. I want you guys to prove that z will be cosine of pi plus I the sine of pi. Then we also have another 2 properties that you must know. When you have z equal to r1 cosine of theta 1 plus I sine of theta 1, so z times w will be r1, r2, the product will be z1. So this is a theorem. So this is theorem number 1. So you will be required to prove this in the test. Then z over w will be equal to r1 over r2 minus theta 2. So this is theorem 2. And theorem 1. So we'll be required to prove that. Then the other properties. So for all z, w being an element of complex numbers, the modulus will satisfy that z will be greater than 0 or equal to 0. If z is equal to 0, then the modulus, the absolute of this will be the same as this. Z over w will be, so these are just some of the general properties if w is not equal to 0. Then the real numbers of z will be less or equal to the real numbers of z. So I suppose that you're gonna check these properties. Z times the inverse of z will be z squared. Okay, so now we've got the inverse of a complex number. So z times z inverse is equal to 1. So I will want you guys to prove this. So this is an exercise, you'll prove it. So you're going to say let z equal to a plus ib, and then w, you let it to be a over a squared plus b squared minus b over a squared plus b squared I. Then you'll perform zw. Then you must get 1. So I'll leave it for you guys to try. Then we've got what we call the Euler formula. Then we'll discuss this one on the next class, because I don't want to have a lot of stuff here for this session. So yeah, and then we'll also discuss the De Moivre's theorem. So I'm just going to write the formulas. Cosine of n theta. Okay. So yeah, for now I'll just write this. Then you guys will continue on the next session from here.